Let's start. My talk is about wireless communication in complex media. And this is really important today for the 5G and even 6G for the future. And I will show you that new material can be used to improve largely the way you can communicate it in complex media. First, I want to recall you that when you send radio waves or microwaves in a city or in a room or in a forest, it's not free space. Waves will interact with each buildings or each object, and wave will be scattered. And the wave field that you will observe depend on what we call multiple scattering regime. There is a lot of scattering between each element in the city, and there are multiple reflections. In fact, a wave field is the sum of all these scattered waves. And for example, this is well known in the case of optics. If you send a laser beam through a glass of milk is made of many scatterers. And when you look on a screen, the light is what we call speckle light. There is a lot of bright spots. These are places where the light is strong, and there are dark spots where the light is weak. And in fact, when you see this kind of figure that results from the interaction of light with a milk, you can define what is called the coherence length, the distance between two bright spots, and the coherence frequency. If you change the frequency of light from red to blue or from red to green, it will change, the speckle will change completely. And these two concepts are very important. This is not only true when you send light through multiple scattering medium, but also when you send light or waves in a cavity. It may be what we call random or chaotic cavity, like a room, and the interaction between light or between microwave and on the wall will give you a pattern where you have bright spot and dark spot. And there is also a coherence length that gives you the distance between two bright spots. And also when you change the frequency, suddenly what we call these eigenmodes change completely. And there is also coherence frequency concept. Now, when you want to control a wave, for example, a microwave that you send in such a medium, you can use the active antenna made of many elementary antenna that you can control, each in transmit and each in receive. It may be a two-dimensional array of antenna. And what is important in this case is to define what is called the transmission matrix. It tells you that if you have all your transmitted antenna, alpha, beta, gamma, and if you go through a complex medium, if you have many receivers like your smartphone, you can define at each frequency for each of these multiple input and multiple output transmission matrix, which is a matrix made of complex numbers that depend on amplitude and phase that you have through this complex medium for each couple alpha, this antenna, and beta, the receiving antenna. And now, if you want to understand how you can improve communication in such a medium, you can think of the following. Imagine that you have multiple antenna. Here I put 1, 2, 3 antenna. And imagine that you want to send a message, a clear message to point R behind a scattering medium, like here. Imagine first that you have only antenna R1 that emit a sinusoidal signal from this point. At point R, you will receive H of Ri R, which is an element of the matrix that I defined just before. And if you look on a screen, you have this speckle pattern. This is the modulus of your field. And of course, you have a modulus map, but you have also, at the same time, a phase map. And the phase between this point through all this multipath and this point is a kind of random phase. Now, imagine that you have another antenna that emits. You have another speckle figure here. And if the two antennae are at a distance bigger than the coherence length, these two speckle patterns are completely uncorrelated. If you have a third antenna, R3, completely different pattern. Now, these are the modulus of the field. And when you send with the three antenna together the field, when you make the addition of all this field, it's also a complex number. And here we present the modulus, but there is no focusing. You have also a speckled pattern. Why? Because for the point R, the phase that you have coming from R1 is here, the phase coming from R2 is here, and the phases are completely incoherent. And when you make the summation, nothing appears. You have always a speckled pattern. And you have to take into account this. Now, due to spatial reciprocity, you have to know that the transfer matrix between R1 and R is the same, but between R and R1. Now, if you want to improve communication between all these three antennas and this point, what you have to do? You have now, instead of sending exactly the same signal with the same phase from each of these antenna, now you have to use the complex conjugated of the transmit matrix between point R and R1, and you send this here. Now you send this here, you send this here with all phase conjugated. That is to say, all this signal has an amplitude which is different and a phase which is different. Now, if you are doing this, when you make the summation, now suddenly you completely compensate all the phase, and because of this, now all the phase add together here, and all these complex numbers suddenly give a focal spot. And the focal spot size has the size of 1 grain. And as you have more and more antenna, which what you call spatial diversity, you focus better and better, and you concentrate energy to send a message here which is clear. Now, this is when you have many antenna and at one frequency. But now there is another case. Imagine that you have only one antenna, but now you send not a sinusoidal wave, but you send a short pulse. And we will speak of frequency diversity here. Now, if you send a short pulse, this is this very short signal in time. If it is a symmetric signal, it results through the summation of many different frequencies with different color, all in phase, and the summation of all these give you a peak. This is what you send. And you have only one antenna now. And you look what you have at point R or on a screen. For color blue, you have a speckled pattern here. For another color, red, if there is a frequency decorrelation between the two, the speckled pattern is completely different. For another color, green, the speckled pattern is different. Each of these figures oscillates, one at frequency omega 1, one at frequency omega 2, one at frequency omega 3. When we make the addition of this, it will be the summation of this, each oscillating at its own frequency. And this is something, this is a signal that at one point is completely random in time. Now you have sent a short pulse, but now what you receive here is all the frequency, but now all the phase of each frequency are uncorrelated. These are the phase. This is a Fresnel vector that gives you the amplitude and phase, but the phases are random. And when you make the addition of all this sinusoidal signal with random phase, it's a signal which is spread in time. And the time can be very long, and it is due to the multipath that you have in the medium. And this time is very important because it tells you what is the reverberation time in your medium. Now, imagine that instead of sending from this point a short pulse, now you decide to send each of these frequency, but making them phase conjugated from the signal you have recorded at each frequency between R and between the 2 points. Now, when you are doing this, by doing phase conjugation for each frequency, it is like you do a time reversal of the signal you have received before. You take this signal, you time reverse it, and now you send it back. When you are doing this now, if you look what you have here, you have all these speckled figures that oscillate, but the phases are different between each of them. And there is a magic time where suddenly all this signal become in phase in the time domain. That is to say, suddenly the long signal you have sent now become very short and very compressed in time. And you have what we call temporal focusing. All this long signal through this medium now give a short pulse. And you have also a spatial focusing whose size is the size of 1 grain of a speckle. And if you want to know what is the efficiency of a process, you have to know how many uncorrelated frequencies you have in your spectrum. If you have many uncorrelated frequencies, you have many spectral degree of freedoms, and you have a very nice concentration. And here, notice that you have only one antenna, which is omnidirectional, but it's focused because the medium acts like a lens. And it is the size of a medium that gives you the size of a focal spot. When we have observed it, and when you see this, you understand that when you want to do communication, you have 2 kinds of degree of freedom. Spatial degree of freedom, it tells you how many antennas you have at a distance, each of them bigger than the coherence length, and how many frequency uncorrelated you have. And when you have all this spatial frequency degree of freedom, you can have a gain in amplification by using all this in a clever way, by doing time reversal, to improve your focusing. You have a tool that you can play with. We have begun to play with this long time ago when we were working with ultrasound. We were working with ultrasound array. It's like microwave, except it's a mechanical wave. And we were working at frequency of the order of megahertz instead of gigahertz. And we have done this experiment, which was quite interesting. You have a source sending a short pulse through a random medium. This random medium is really a forest of steel rod that completely broke all the coherence of your pulse. You record with many antennas your signal. These are long coda in the time domain. Now, you take all this signal, you time reverse, and you send it back. And when you look how the time reversal process go, you can look what is the size of the focal spot you have here, and what is the signal that you receive at the initial point when you are doing this. You see that when you send all this long signal, in our experiment, all this, when it comes back here, are compressed. You have completely canceled all multipath. Second, when you look what is the size of a focal spot, by moving your antenna here, you see that the size is very thin. In presence of this random media, you see that the size of a focal spot is here nearly 30 times thinner than the size of an antenna that has this dimension through free space that focus here. You see that the medium become a lens. It is like, it is not this antenna that are the lens that focus here. It is the medium itself because of time reversal that now focus. And you have a very thin focal spot. But now you can use this to do communication. Take 40 antenna here and decide that you want to send 5 different messages to 5 different people, very close one from the other, typically at one wavelength, one from the other. And use the concept of time reversal. Excite all these, receive a signal, and time reverse. If you time reverse through this random medium, because you have the super resolution effect, you can focus independently on these 5 antenna. But now, if you take this medium out, you have your 5 antenna, you send signal, you time reverse, you send back, and now you will eliminate all antenna together. And now you can send different kind of message to different guy. And we have done this by sending a lot of data to these 5 different guys. When we have the medium, which is here, the communication is very good. There is a very small error rate. But now when you take this out, communication is very bad because what you send here overlap with what you send here. There are interference between all these. Multiple scattering can be strongly improved through complex media by using time reversal. Now you have a concept which is quite important. It is the concept of Shannon capacity that tell you what is the maximum rate of information that you can transfer per frequency. You know this very nice theorem of Shannon that tell if you have one source and one receiver, the capacity that you have that tell you how many bits per second and per hertz you can send in an optimal way without error is given by this formula where rho is the signal to noise ratio. Of course, the signal-to-noise ratio depends on the noise you have here and of the strength of the signal you receive. And this depends on diffraction of your wave. What is the level of the wave? Now, this formula can be generalized when you have many antennas that transmit, many that receive. This is called MIMO, multiple inputs here, multiple outputs. And for example, at one frequency, you can see that the number of bits per second that on one per hertz that you can send, this is a very nice formula given by Bellatar. You see that you have also the log, but now something appears here. It appears that in the determinant that you have here, you have H, the transfer matrix, multiplied by H DAG. H DAG is the reverse matrix plus conjugation. And H DAG is what we call the time reversal operator. If you send a signal from here, when it comes here, if you time reverse, when it comes back here, it is H DAG. And you see that the capacity now depends on this determinant of H DAG. H DAG, if you look the singular value decomposition of H, you will see that here appear what we call the singular value of H. How many singular value I have in this medium through a propagating medium? And here, if I have many singular value, for example, if I have 40 antenna and 40 antenna, how many singular value I have? I have 40 singular value, but how many singular value are strong? These are the channel that I can create through this medium. And if you have, for example, 40 antenna through a medium which is a free space without reverberation, here I have 6 singular value. But when I put my random medium, like I explained before, now I have 34 singular value. That is to say, I can send more information in this medium. And here, if I look, this comes from the fact that I can have much more focal spots which are independent when I have here a random media instead of having a free space medium. I can send more information when the medium of propagation is random, and this is important in CT, and I will come back on this. All this nice idea on MIMO now are can be used in the concept of electromagnetic wave and not an ultrasound like we have done. And we were the first to do this with electromagnetic wave. And we show that for electromagnetic wave in room, we can also focus very nicely on very small spot to send different information through a complex medium. Now, all this to be very interesting, it's need to have both spatial diversity and frequency diversity. But frequency diversity today, it is too expensive. It needs ultra-wideband communication. And today, people work only with spatial diversity in 5G. Frequency diversity is not big. People use relatively narrow band signal, typically 50 megahertz around 3 gigahertz, which is narrow band. And in fact, they have no spectral diversity, but only spatial diversity. And 5G used this concept to focus wave, but only with spatial diversity and with kind of phase conjugation technique. But it is quite expensive because you need many antenna to do what is called massive MIMO, and many antenna with many amplifier and many emitter. Now, we try to find something better than using many antenna to improve communication for when you are relatively narrow band. And we found this idea 8 years ago in our lab. Instead of focusing in an active wave, we will do a passive control of the wave by using tunable metasurface. And this is the concept I want to explain now here. Imagine that you are in a room. Imagine that point A wants to send a message to point B perfectly, without loss. If you are in a room, which is an ellipsoidal room, and if point A are at one foci and point B at another foci, all the signal you will send in all directions will be reverberated and refocused exactly in phase at point B. This is the property of an ellipsoidal things. But you are not in this kind of room usually. You are in a random room. And imagine now that instead of being in this kind of ultra excellent communication system. Now you are in a room and you are at point A, want to emit a signal to point B. But imagine that now you put on the environment a controllable boundary. And this is what I call the tunable metasurface, which is half the wavelength that you used. And each element can have a reflectivity that can be controlled in phase or even in amplitude. Now, how can I play to maximize communication between A and B? In fact, imagine that you are in a room with, you have obstacle, A and B want to speak perfectly one with the other. Imagine that here you have your boundary where you can measure the field emitted by A. The field emitted by A is one element of this transmission matrix, and it is an amplitude for each point Ri and a phase. That depends on all the multipath you have. The same for B. Now imagine that now this surface is a mirror which has a controllable reflectivity that depends on the position, which can be an amplitude reflectivity and a phase reflectivity. Now, if you build a mirror that has a reflectivity which is the phase, which is H conjugated coming from A, you have built a phase conjugated mirror. And when you send a signal from A, whatever is the complexity of the medium, everything comes back to A. This is a phase conjugated mirror with this reflectivity. Imagine that B sends a signal and you know the field, and now you build a mirror which H conjugated as a reflectivity. Everything will go back on point B. These are two-phase conjugated mirrors. This is not what you want to do. Here, what you want is that all what you send from A focus on B. How to do this? Very simple. You have just to build here a mirror whose reflectivity is the product of the phase conjugated mirror to go back to A and the phase conjugated mirror to go back to B. If you do this, when you send a signal, all the phase that you have here and that come back here are put in phase. This will exactly focus back here. And all the elementary waves that come on each are reflected exactly in phase to come back on B. But you have also what come directly from A to B through obstacle without going through this mirror. And it is another vector. And now, if you want to perfectly match these two vectors, you have to add a phased shift, the same for all these elements. And if you do this, this will give you a big signal on point B. Now in this room, you have make a perfect connection between A and B to send a flow of data. And now, to build this kind of smart mirror, we make two assumptions. First, we make only a phased-only mirror. We don't control the amplitude like we can do. It is only a mirror that changes the phase. And now what is really important is that we used binary phase mirrors. It is a very simple mirror that when it receives a signal, or it reflects with +1 or -1, where it phase 0 or phase pi. And a binary phase mirror is enough if the number of pixels is big enough. It will be enough to refocus here. I will not explain you the mathematical theorem about how a two-phase mirror works compared to a perfect phase mirror. But as the number of elements is bigger and bigger, it's become really very attractive and very simple to build. How to make a mirror that can be a two-phase mirror? And it is very simple. We take a piece of epoxy and this is for electromagnetic wave, and we put on this mirror that you see here, every λ/2, if we work at 2.4 gigahertz, it is 6 centimeter λ/2. We put a small resonator, an electromagnetic resonator, a flat resonator. And all this mirror, it is like you have a ground plate here, plus your resonator. When an incident wave comes, if you send a signal which is at the same frequency but your resonator. You know that when you are at resonance, the resonator shifts the signal for pi/2. An incident wave is shift of pi/2. After there is the mirror, it shifts from pi. And after it come back on the same resonator, it shifts of pi/2. This is what we call state 0. All what come back in phase. Now, imagine that you have a small parasitic resonator with a diode, and when we make a short circuit, suddenly you change the frequency of your resonator. Now you are in this case, state pi. You send something, it goes through this, and there is only a pi shift. This is a two-phased binary surface. Now, this is here the small circuit that you can design, and we design many other. And depending if the diode is in short circuit or not, you have this shift of pi around the frequency here of Wi-Fi. Now, if you put on your wall some of this kind of mirror, and if you decide to improve communication to this guy, which is here, and you have an antenna in another room, you can do what I explained. You can find what are the best phase to focus back on this. But you don't need to do all the measurement of the phase coming from this antenna and this antenna to do this. You can do just an adaptive algorithm. You try a phase pattern with some configuration. You look on your smartphone what is the level of signal, and if the level is not good, you change one element and you see how it change. And you do this iteratively, but you have not to try all configuration. It is too much, because the spatial correlation of the wave field is λ/2 in a room. You can try a small number of configuration, and the system learn how to focus on your smartphone. Here, you have your mirror here, and here, oh, sorry, you have here, you will have an antenna here, and you look what is the level of signal you have, and you change the configuration here. This is the pattern that you have. And now, if you move your antenna at a position where there is no signal, the system learn how to refocus back. Here, it is very slow because it was just all the experiment done in the lab, but the system tried to find a better configuration to focus on your smartphone. Now, we make a startup with Geoffroy Le Rosey, which is called Greener Wave, to build this kind of metasurface at different kind of frequency, from all different frequency that are used in 5G for different configuration. And now, what is the most interesting is the following. Here I explain how I improve the communication between alpha and beta, two antenna only. But now, if I want to use MIMO configuration, that is to say I have many antenna that transmit, many that receive, even in a collective way, I can look, if I have a propagation medium, which is my room, it is not a perfectly random medium, as you remember, to improve the communication. But now I can add on the boundary of this medium my control lab metasurface. And I can do the following. I am in a room, I have, for example, 4 or 8 antenna that transmit, like MIMO configuration, and 4 or 8 antenna that receive. And initially, my room has this boundary. It's not a perfectly random room, but I put some surface on it. And I decide to change my configuration to maximize the value of my singular value. What I want is to have the maximum number of singular value, and I want to have all the singular value equal, because when I have all the singular value equal, the Shannon capacity become maximum. And I can have an algorithm that change the configuration of my room and of my multipath to maximize the Shannon capacity. If I have a completely random room, I will have channel, my singular value decomposition is a big channel with smaller channel. It's not perfect, but it gives many channels. But what I prefer is to have equal channel. And what I can do, I can change my metasurface configuration in my room to maximize in a 4x4 MIMO configuration the value of my singular value. And when all my singular value reach the same value, I can just use time reversal technique through this new room, which was changed by maximizing this, and I will have a better communication. And in fact, we begin to work on this in 93, 94, when we published the first paper to explain this concept. Nobody was interested by this shaping complex microwave with binary tunable metasurface. When we published in 1999 that this worked for multiple channels, and we published after a general paper that say this idea is ready to come, suddenly people were interested by this. And till 2020, there was nobody working on this. And when we begin to publish this, there was just in 2020, 400 papers on RIS. RIS is reconfigurable intelligent surface. LIS is large intelligent surface. Now, many people are interested by this. And now, the problem that people think, and this is quite interesting, instead of using base station with many antennas that send a lot of energy and consume a lot of energy, if you have some building, for example, where you have this reconfigurable intelligent surface, and if you have in your building some reconfigurable intelligent surface, you can maximize the spatial diversity to focus better and to have quite better ratio between the energy you send from your base station to the information rate you obtain here. And now people are defining many algorithms to improve when you have M base station antenna plus this reconfigurable intelligent surface, which has n elements, plus your smartphone. What are the best algorithms to maximize the information that you can send? And this is really think as a 6G technique. And many people are working on this. Now, there were different teams that rediscover what we have done in 94. For example, MIT, they published a paper in 2020. They made a reconfigurable intelligence surface with 3,200 elements, and each element is or a reflector or an absorber. They lose half the energy, but it is a kind of reflecting surface like we have. And now it is really a field that is growing, and many people are really working on this. And all the big companies are beginning to look how this metasurface can change the way you send information. Remember, the base station going directly to the user, if you have not a reverberating environment, the spatial diversity is not very good, because many times each element of your antenna of your base station are too close one from the other to be completely uncorrelated. And you send more energy, but it is not well focused. 5G is only base station too smart to user. 6G can be base station plus passive wall. This passive wall can be controllable. They don't need energy. It is a very small amount of energy you need to change the resonance frequency of your element. It's a very low energy consuming things, and the electronic is very simple. It's only a digital electronic without the complexity of a very high frequency electronic independent for each channel. And it can really change the way you maximize the information that you can send in a medium. Here, for example, this is for 30 gigahertz, this kind of surface that you have. And in fact, the system has two polarization. It can reflect electromagnetic wave with pi or 0 for the two polarization. And you can control this completely by changing the configuration of phase. And you can hear it is more a classical phased array, except you have only one antenna and it is only a mirror. And we can use this technology to make also satellites come antenna that can track satellite very easily with many of these elements. Now, all these concepts are interesting for microwave, and if the price is become very weak, that will come in the future, you can recover many surfaces that become intelligent for microwave. You know that we have glass that are intelligent for light. A special glass can change its color or its configuration for light. Now, this will change the environment for microwave. Now, all these concepts that were defined for microwave, we can also look on them for sound wave. And I work also in Hong Kong with, and there we decided to develop a smart wall for sound wave. And it is also a wall that can change its configuration. It is made of many cells. Each of them can be hard or soft. And for example, you have a source sending noise. Here, it is not a mirror, it is a transmit wall. And you decide that you want to kill the sound here. And you can, with an algorithm, try to find what is the best configuration of your wall from hard to soft to kill the sound here. And the wall is made like this. It's a little bit complex. But now we have different ideas how to make a smart wall. Here it is a transmit wall and not a mirror wall, but we are working now in France in our lab to make also a mirror wall for sound wave. But the problem you have for sound wave is that you need a wall that can control sound wave with a broadband sound, because when you speak, you don't send only one frequency, you send many frequencies. And we are thinking to build an active wall for sound wave that can control the sound that somebody who speaks in the room, what he say will go only to another guy and nobody else will hear what he say. And we can imagine this kind of wall, and we are looking for this. I just want to finish by telling that we have created a company, Greener Wave, from this technology, especially for microwave, and we call this green. Why? Because in fact, you can use base stations that send much less energy, and it is good for ecology. You have not a big value of the intensity close to the base station, but if you use just at a good location, smart wall that change the environment, you can maximize the communication. Thank you for your attention. Thanks.